Hi, I'm Kenton. I'm the architect of Workers. I joined Cloudflare about a year and a half ago and was given this challenge of, we want people to be able to run code on our edge network. How are we going to do that? And I'm going to tell you a little bit about that, but you've already heard a bit about how you could actually use Workers. And what I really want to tell you about is what I think serverless will become in the future. So I have to admit something. I have a problem with the current generation of how serverless is done today. I don't think it's living up to everything that it could be. I mean, it's great that you no longer have to worry about how to deploy servers, how to scale and all that. You can just write your business logic and send it out somewhere. But there's really something much more that could be unlocked by this change. So I want you to think a bit about the unit of servers, of compute over time. So back in the 90s, Alta Vista, big search engine in the 90s, it ran on a mainframe. And in fact, Alta Vista was created as a big old advertisement for this DEC mainframe. The idea was you'd buy a big mainframe, and this is how you would handle a big site that handles lots of data and lots of traffic. And then Google and some other people came along and said, we can actually do better if we separate our servers into smaller units. We're going to actually just use commodity computers to run our servers, and we're going to network them, and we're going to use clever software to be able to combine them into sort of one supercomputer and get some advantages out of that. It's more flexible because now we can add more computers to scale up. We can write clever software that's fault tolerant, so if a computer dies, it's fine. And it's stuff like that. So one mainframe could kind of be replaced by 10 to 100 computers, commodity computers, depending on whether or not you're talking to a DEC salesperson. So we'll say 10. And then a little while later, a couple of years later, VMware came along and said, well, this hardware is actually not being fully utilized. You often install a server on a computer and it's using like 1% of your CPU. This is kind of a waste. But the problem is that if you're trying to install multiple servers onto this machine and other servers on this machine, it becomes kind of a pain to manage those separately. But if we could separate them into virtual machines, use software to make one physical machine look like 10 virtual machines, then we can manage those independently, install separate software on them, even move them around between physical machines. Things become, again, more flexible and easier to manage. And a few years later, Docker comes along and says, well, we can do better than that even. With a virtual machine, you have to sort of allocate a specific amount of resources to start with, and that's what it is. With containers, we can not only have less overhead per thing we want to put into this machine, but if one container uses less resources than were allocated to it, then those can be used by the other containers. And you can basically fit even more into one machine more easily. But now we're saying the unit of compute is a single event, a single HTTP request, or a single invocation of your serverless function. So we've seen this series of 10x increases in granularity so far, but what is the increase of granularity between a container and a single event? Well, say a typical server might handle 500 events per second. There's 86,400 seconds in a day, 30 days in a month. You usually build these things on a monthly cycle, so I'm saying a month. And that comes out to somewhere around 1 billion. So on this scale, the whole difference between mainframes and containers is 1,000x. And the difference between containers and events is 1 billion x. It's 3 times over. You would expect that this means that there are some big differences in how we think about server infrastructure, how we think about cloud services and how we organize them today. But so far, the differences haven't been that great because so far, there is no serverless. Serverless is just someone else's container. What it has meant so far is someone else is going to start up a container for you and run a traditional server stack and run your function in it, sort of hide these details from you, but they're still starting a whole container to run your code. And that means that there's costs involved in starting up that container. It takes a certain amount of resources, and they have to make sure that that one container is going to run a lot of events in order for it to be cost effective. They can't just start up that container to run your function once and stop. They're not going to make any money that way. So the services encourage you to centralize your compute, even though you're thinking about individual events. And your serverless code is still running in a mega data center somewhere. You might be given a few options, depending on the provider. It might run in 1 place, 4 places, 12 places around the world. But it's still running basically the way that traditional servers have run for some time. And what I want you to think about now is, what if we had a technology where you could run just one event, invoke your function once, start up your code, run it once, and shut it down, and that was fine, it was efficient, it was cost effective? How would we start doing things differently with this kind of technology? So I think what would happen is, instead of running your code in one place, now you can run your code everywhere. You can run each event at the place where the event was generated, even if that's thousands of places around the world. And instead of thinking about consolidating compute around whose code is running and what code you're running, you can start consolidating around other things which make more sense. So I'm going to talk about 2 such things. One thing is you can co-locate services from many different providers into one place. So modern cloud services are often built on a stack of other people's services, all bound together with event handlers and API calls and such. And usually you're calling out to their servers across the internet all the time. Let me just give you a little example to think about. So say you have some sort of a service where someone can send you an SMS to purchase something. And so the user is going to send you an SMS message, go to their mobile carrier, and then say you're using Twilio to handle, to receive SMS. And so it goes to Twilio's servers, and then they send you a webhook, which is going to go out to your serverless function running somewhere. And your serverless function now wants to charge this person money, so now you're going to use Stripe as a great API for payments. You're calling out to them. Stripe will generate events when things happen. One of them is they will generate an invoice event when someone has a new invoice you need to send them. Say that's going to go to another webhook, to another serverless function you've written. And there you're going to send an email to them. That goes to, say, Gmail, which then forwards back to the person's mobile network, and eventually it returns to the user. Now, this is actually a fairly simplified example. Obviously, services today can involve way more layers than this. And every single one of those arrows there is a trip over a network, potentially over the internet. And that's kind of a problem because the internet, there's latency involved. The internet's not really going to get any faster in terms of latency because the speed of light is a constant. There's bandwidth costs involved. We're congesting internet backbones with a bunch of messages that are just like lower layer service messages and that don't feel like they really belong there. And it's a reliability problem because these links go down sometimes, and every time you're sending another message over a link, you have another chance for that message to be dropped somewhere and for the result of the operation to be an error. But now, if we can run our serverless code anywhere, like you don't care where your serverless functions run, you just want them to run. This is just your business logic. The whole point of using serverless is to let other people worry about where it runs. So where's the optimal place for your functions to run in this example? Well, if Twilio is sending you an event and you're responding to that, maybe your code should just run on Twilio servers. And if Stripe is sending you an event and you're responding to that, maybe your code should just run on Stripe servers. That would be the first step, but I think we can go even further. If everyone's writing serverless code, if all of these services are based on serverless code, we can potentially take all of them and consolidate them and run them on one machine. Perhaps literally the machine in this cell tower that the user is communicating with, or something nearby. And now all these links are local on the same machine. They're perfectly reliable. They have no latency. You can send all the bandwidth over them you want, pretty much. And now you can compose your cloud services out of many more layers and not worry that you're adding this additional cost in the meantime. The other thing that we could take advantage of a lot more is geographic affinity, which means having code run near the users that are invoking it, and especially when there's a large group of users who are collaborating on something, having that be near them. This could mean anything from like 5 people in an office building collaborating on a document in real time using Google Docs. Their keystrokes shouldn't have to go across the world before each other can see them. But I'm going to give you a slightly different example. So in the future, perhaps your dog will be walked by a drone. And this drone needs to talk to the internet, obviously. It needs mapping data to figure out where to take your dog. But it also needs to coordinate with other drones in the area so that your dog can meet up with other dogs your dog likes and hang out together and have fun. But also importantly, your dog does not want to run into that one dog that your dog hates. Look at everyone hates this dog. Look, he's up there. Thinks he's better than everyone else, looking down on all the other dogs with his drone that's so powerful he can carry him up there. So how are they going to do this? Now, you might say, well, all these drones are nearby each other. They could form a peer-to-peer mesh network and not use the internet at all, right? But there's a problem with that, which is that this dog's drone has bad firmware. And whenever it gets on the network, it keeps electing itself master of the local consensus group and then dropping all packets. So basically, there's this black hole in the network that moves around with this dog, and none of the other dogs in the area can communicate when he's nearby. Peer-to-peer is hard because users' devices are unreliable. People close their laptops. Their phones run out of battery. So you really need a client-server architecture. It makes everything so much easier. So we're going to have a server, and all the drones are going to talk through a server. But where is that server? Is that server in Virginia? And what happens when you have a bunch of dog-walking drones in New Zealand? Do they need to coordinate all the way back to Virginia to find each other? Well, that's kind of dumb, but you know, if this this drone is being sold all over the world, maybe they've set up servers in several locations, which will typically look something like this. You have servers in 5 places, 2 in North America, 1 in Europe, 1 in Asia, maybe 1 in Australia. And so now their server's a little bit closer, but for those dogs in New Zealand, they're still talking over a body of water just to communicate with drones that might be a block away. That doesn't feel like it should be the case. What you want is something more like this. So imagine if you could take your code, your serverless code, where you don't care where it runs, and just have it run at whichever of these dots is closest to the users talking to it, just automatically. So this is Cloudflare's network. The purple dots are where we are today. The others are where we're going in the next few months, and we'll be accelerating after that. But if you don't care where your code runs, you should just be able to deploy it to all these places. And And that's what we've built with Workers. So in order to do that, though, it was necessary to rethink the server technology. So we can't just take containers. We can't just take off-the-shelf server stacks and put them in containers and give you a container in every one of these hundreds of locations. Because your code, when you deploy it on Workers, actually runs in every single one of these locations. We need a way to be able to actually run just one event, like receive one request and start up your code instantaneously. Stephen mentioned cold start times. Have that be so short that we can run just one event and it's fine and it returns quickly. And yeah, sometimes we'll handle a few events with that instance. But if one event runs fast enough, then a few events is even better. We need to be able to host thousands of customers' code on one machine, because instead of one mega data center, we're talking about hundreds of smaller data centers. And we need them to all be securely isolated from each other. So what kind of technology would allow us to do this? It's not the existing containerization systems, it's not the server technology, but it turns out that people have actually been doing this kind of stuff for quite a while. People who have been doing it are the browsers. So your web browser can have, some people have hundreds of tabs open at a time, and each of those tabs has a bunch of iframes, most of them with ads inside them, but iframes nonetheless, or Facebook like buttons. And those are all like separate JavaScript contexts, sandboxed from each other, every single one of them. And they load fast because your browser downloads code and wants to start it up as quickly as possible because you're sitting there waiting for it. And they don't take much memory. So what we did was try to see how we could take this technology and adapt it to be a new generation of serverless platform. And basically we took V8. V8 is the JavaScript engine from Google Chrome. Could have taken SpiderMonkey or Chakra or these others too, but V8 has really seen the most use in these kinds of alternative use cases. And it's been around for 10 years. People have been trying to find ways to hack it that entire time and found a few, but it's been hardened. And it's really fast. Google it's making it faster all the time. And they're really focusing on these cases of fast startup and then even faster long term. So we built a new server stack on top of V8. Now you may have heard of Node.js is also built on V8, but Node.js is not designed to run multiple users' code in separate sandboxes. And it's not designed for incredibly fast startup, though it is pretty fast at starting up, in part because it uses V8. But it's not its intended use case. We had to build something new that could actually solve all our requirements. And we've come up with something that actually can start your code in under 5 milliseconds, handle that event in under a millisecond, only takes a megabyte or two of memory per user, so we can have thousands on one machine, and is secure. But there's still one thing missing. So storage. I showed you that example of the message passing between all the different services and said, well, what if that could all be on that one cell tower? One problem is that all those services, of course, have some state that they want to keep with them. So we need to figure out what is serverless storage for storage. Today, it's usually you talk back to some more centralized database somewhere else. So we're not quite there yet. But let's dig into this a little bit. So this is what using Cloudflare used to look like before Workers. So you have your users, they connect to your website through Cloudflare. Cloudflare has a location nearby that can cache your static content, so all your static content serves them quickly. Whenever they access anything dynamic, then it has to go all the way back to your app server, wherever that is, and your app server is usually close to your database. But with Workers now, your application can actually run in front of the cache because it also runs at Cloudflare's edge. And this is really cool because now you can use the cache a lot more effectively and serve even dynamic content very quickly. But you still need a database somewhere, and that still tends to be far away. And you can kind of make up for that. So if you're really good at caching your reads using a local cache, and if you, for writes, you can do them asynchronously so the user doesn't have to wait for them to complete. You can make it look like everything is operating very close to them with no latency. But there's a limit to this, and there's a thought experiment that I like to think about when thinking about this problem, which is, what happens when people go to Mars? So what happens to the internet on Mars? Oh, there, I've got a Unicode box there, cool. So let's say we've sent people to Mars, and let's say we've sent a Cloudflare data center with them. So why not? So now people on Mars want to use your cloud app, which is using Cloudflare. So they can run all the code there, but the database is still on Earth. If they try to access anything that's not in the cache, they're going to have to wait between 6 and 45 minutes for that response to come back, depending on the current orbits of the planets. And that's just completely unacceptable. That does not work. We have not solved this problem yet. Elon Musk isn't going to like this. So what do we do about this? And you know, it's easy to, you might say, well, Kenton, I don't care if my code runs on Mars. There's no one on Mars yet. Why are you telling me about this? This problem exists today. This is a thought experiment, but it's designed to make us realize a problem that exists on Earth today, which is that Mars is basically New Zealand. New Zealand's far away from everything. The internet is slow there. We all forget about it because we're not in New Zealand, and for us, the internet is fast, and it's easy to forget about them and say, well, you know, so they have a couple of seconds of latency. They can still use this service. It'll be fine, right? And what can I do about it? Well, I want to solve the problem for the people of New Zealand and the people of South Africa and the people of Chile. I want them to have just as fast applications as the rest of us do. So we need this serverless for storage. And the way I think that's going to look is, what if we took our central database and split it into pieces, separate databases, say for each user, so that each user's database could be close to them. So when they're accessing their own data, it's fast. And only when they have to communicate with other people's data or coordinate, then it has to go back to the central database. Then what if we take another step still and say, actually, let's not have a central database. Let's only have the user databases, and they can talk to each other in a federated fashion. If we can do that, then now we can have the people on Mars collaborating with other people on Mars, people on Earth collaborating with people on Earth, all using your application seamlessly and not have a problem. And Elon Musk is happy. If they have to communicate between the planets, there's still a problem, but at least people on Mars can basically use the internet. This is what I'm working on now at Cloudflare. It's a very interesting problem. It's not really a thing that has been fully solved before. We have some ideas that no one's really tried before that we're trying. Unfortunately, not ready to tell you about the details yet, but this is very excited about it. Mostly. So yeah, so if your code can run, so we have, it is said, I haven't checked it myself, but supposedly we have data centers within 10 milliseconds of latency of 90% of the world's population. So if your code is 10 milliseconds away and can run there, then yeah, obviously you're saving that. Users will travel around, and the solution we're working on would allow data to move around as well. Of course, the larger the data, the harder it is to move it quickly, but basically we want to have a system where data doesn't permanently live in any particular place. It sort of adaptively moves to be closer to whoever's accessing it. You can run code in the user's browser. Why would you not run all of your code in the user's browser? Well, the problem comes when you have things that need to be secure, like if you have to authenticate the user, you don't want to do those checks on the user's browser. Or if you have collaboration going on between multiple users, you want to make sure one user can't mess up the data for others. Or when you need reliability that isn't provided by an end user's machine. If you want, one user is going to produce some content and then others are going to view it, you can't expect that first user's machine to stay on to serve the content long term, so you need to have a server somewhere for them to talk to. Or like in the example I gave with the dog walking drones, there's the drone whose firmware is unreliable and messes up the rest of the network. If you can avoid having peer-to-peer consensus and instead have a server that you control as a service provider, you can make it much more reliable. Well, you may have been a fan of my previous company then, is Sandstorm, personal server framework, which is all about running your own personal cloud on your own machine. But I mean, civilization is built on delegation. And at some point, we do have to trust each other unless we want to, each and every one of us build everything from scratch and grow our own food. So you can, I certainly admire people who want to self-host their own servers, but it's a lot of work. And at some point, maybe you can deliver more value by paying someone else to have those data centers in 150 locations around the world already set up to do it for you. But yeah, I mean, that's a never-ending debate, I think. Yeah, so you can use, it's kind of like developing for a browser. You can use tools like Webpack or Rollup to package NPM modules into your one combined script that you upload.
So you can use all NPM modules?
It depends on what APIs they need. So we don't provide the full set of Node APIs. We provide more browser APIs. So if you want to, for instance, do an HTTP fetch, you have to use the fetch API, which is something that exists in browsers. And a lot of stuff has been, works on that these days. We do like to implement standard APIs as standardized by W3C rather than inventing our own things. And so that makes it easier to take existing code and make it work. But sometimes you have to port some things. You currently cannot do that with workers. Okay. When an HTTP request comes in, you can use up to 50 milliseconds of CPU time. Okay. Which doesn't include time waiting for other servers. It's just the time spent actually executing your code. And then you're done. We would like to provide more facilities for bulk compute in the future. Yep. There's different trade-offs that happen there. Yep. Yeah, so that's the challenge. Each of these pieces of data has to have a central point of coordination in order to be able to do transactions on it. So that's why it's so much easier to decentralize read-only data, because you just have caches everywhere. When you need to write, you need to do transactions, you need to decide where is the one point in the world that gets to decide whether a transaction committed or not. And that's basically what we're trying to solve right now, and we're trying to find a way to have it be a potentially different point in the world for each piece of data, and have that point move around and naturally draw closer to the people who are communicating with it. So like if everyone in this room is all part of some raffle, then it should be a machine like in this room or nearby that is coordinating that raffle instead of a machine in Frankfurt. Well, updating code and updating stored data are different. So when you deploy code to workers, we propagate it worldwide within about 30 seconds. And because it can just restart so quickly, now it's live everywhere. For the storage for data, so as I was saying, you need to have some central point that is the coordinator for any particular piece of data. For that central point, there is essentially no delay to do any kind of operation on that data. And then the challenge becomes how does it propagate out from there? I think we're trying to solve a different problem than a lot of those databases have solved. I mean, it would be easy enough to say, okay, we're going to deploy a big CockroachDB instance and worldwide, globally consistent. But that's still kind of a centralized service. And what I really want is something where that solves the Mars problem that I mentioned earlier. And I'm not sure that those existing technologies do that. Now, on the other hand, obviously, I'm not going to build the next spanner. That it took Jeff and Sanjay so many years to get that stable at Google. I used to work at Google, and I'm not going to be able to repeat that. But if we can find a narrower problem to solve that produces something useful without so much complexity, I think that would be cool. So that's one of the big advantages of using V8. And this is why I think the next generation of serverless platforms are all probably going to use V8 and embed V8 or one of the other JavaScript frameworks, because we can actually run a large number of V8 sandboxes within a single process, a single memory space. And that it avoids that cost. It avoids the baseline RAM cost of each process. And that's basically how we're able to host so many people on one machine.